So let's start with this week's tutorial, right? I hope you have already submitted the tutorial in the provided your tutorial solutions the provided Dropbox, right? So let's start. So there's three questions this week, and all of these are focused on the ADCs, right? No, yeah, both ADC and the DAC. So question number one, a 12-bit dual slope ADC uses a 1 megahertz clock with the voltage reference of 10 volt. Its analog input voltage is in the range of 0 to negative 10 volt. The fixed interval T1 is the time taken for the counter to accumulate a count of 2 to the power of n. A. How much time is required to convert an input voltage equal to full scale value? So the full scale value, right? When we say when we use this term full scale, we are basically referring to the maximum voltage that can be used to or the maximum voltage that can be converted. So in this particular case, when we are using a dual slope ADC, so we are using a voltage reference of 10 volt. So the maximum, right? If you see the analog voltage range is also from 0 to negative 10 volt. So the maximum voltage that we are using is 10 volt, right? We are basically converting the maximum voltage that we are converting is 10 volt. So based on the information that is provided by this in the statement of question number one, we know it's a 12-bit system. So we are basically converting how many digits? 2 to the power of n number of values, right? That is 2 to the power of n, which is equal to 2 to the power of 12, which is equal to 4096. So basically we are doing a analog to digital conversion of 4096 different values, right? And we also know that 1 megahertz, right? We also know that the clock that is being utilized, right, for this particular ADC is 1 megahertz. So basically the period of the system is 1 upon 1 megahertz, which is equivalent to 1 microseconds, right? So basically what this means is one particular conversion in this particular ADC takes 1 microsecond, okay? Now, coming back to the question, right? Part A, it says how much time is required to convert an input voltage equal to full scale value. So now, when we are when we are dealing with dual slope ADC, we have something like this, right? The graph will count up, and then it has to reset itself, right? Or it has to count down as well, right? It has to count up and count down. So in order for the system to perform a full scale conversion, right, in a dual slope system, right? Dual slope because it has two slopes, right? That is why it is known as a dual slope system. So for a full scale conversion in a dual slope system, what happens is it has to count up and then it has to count down as well, right? So the first thing is, if our full scale, if we are since we are converting the input voltage of full scale value, right? The input voltage is of full scale value. So what this means, if we are using a full scale value, the maximum input voltage, that is 10 volt, is also equivalent to the reference voltage, isn't it? So in this particular case, when our Vref is equivalent to our input voltage, right? Vref is also equivalent to our input voltage. What happens is the slope on this particular side is also equivalent to the slope on this side as well, right? So basically this triangle that is being formed over here, it is symmetrical, right? So the time taken to count up, right? The time taken to count up is basically equivalent to, we have 4096 different values, and each particular value has needs 1 microsecond to count up, right? So what we do is 4096 multiplied by 1 microsecond, that is going to give us 4.096 milliseconds. So this is the time needed to do a full scale conversion or count up, right? From 0 till 4096, right? Okay, so that is the time needed needed for the integrator, or basically the time needed to count up, right? From 0 till 4096, right? So we need that much time. So if that much time is needed to count up, so since Vref is equivalent to our V peak or VA, that means there will be a similar time taken to count down as well, right? So basically that is, again, we are counting down 4096 different values. So again, 4096 multiplied by one microsecond is going to give us 4.096 milliseconds, right? Or basically what you could have done is also whatever time was needed to count up, that is the same time needed to count down. So whatever time you get, to multiply by 2. This is not always true, right? You also have to be, you also need to consider that what is the maximum input voltage that you are supplying and what is the voltage reference that is being used, right? In this particular case, since our maximum analog input voltage is 10 volt and the reference voltage is also 10 volt, so that is why these two are equivalent. Okay, these two slopes are equivalent, so that is why we can multiply by 2. Anyways, so that the time taken to count up is 4.096 milliseconds. The time taken to count down is 4.096 milliseconds. So you add it up for a full conversion, right? So the total time taken to count up and count down is 8.192 milliseconds. So that is the time required to perform or to convert an input voltage equal to full scale value. Okay, so everyone is clear with that? Are you guys okay with that? Okay, great. So you understand how we get 8.192 milliseconds, right? Okay. Okay, great. So let's move on to part B of this particular question. It says if the peak voltage reached at the integrator output is 10 volt. Again, it says the peak voltage is 10 volt. So 10 volt is basically equivalent to our reference voltage again, right? What is the integrator time constant, right? This is the same voltage that we used in part A as well, isn't it? So what happens is the full scale conversion happened at 10 volt. So that means the time needed to convert this 10 volt will be same again, right? Isn't it? So you can directly take it from this part A question, right? The integrated time constant would be the time taken to count up, right? So this is the integration part, right? Isn't it? So basically you can directly say that the time taken or the integrated time constant is 4.096 milliseconds. Or the other thing that you can do is again, the period, right? The period that is basically 1 microseconds. 1 microseconds multiplied by 2 to the power of n. Again, n value is 12. So 1 microsecond multiplied by 2 to the power of 12 is going to give me 4.096 milliseconds. Remember, the count up slope is equivalent to our integrated time constant. Okay. Part C, if through aging RC increases by 2% and if through aging R increases by 2% and C decreases by 1%, what does the peak voltage become, right? So the formula for peak voltage is equivalent to VA times T1 upon RC. T1 is basically the time from here to here. So basically the time taken to count up, right? So if you pay close attention, it says that the R value increases by 2%. So basically whatever R value we have, you multiply that by 1.02, isn't it? So that means that indicates an increase in 2%, isn't it? All of you agree? So when we are increasing a value, we are basically increasing the resistance value by 2%. So basically we are multiplying whatever resistance value we have by 1.02. What do you think? Guys, you there? Okay. So yeah. So basically when we are increasing the resistance value, we are multiplying the resistance value. Since we are increasing by 2%, it is same as multiplying whatever resistance value we have by 1.02. And the C decreases by 1%. So what this indicates is that whatever C value we have, we multiply it by 0.99. At maximum, it is 100%. So whatever value we have, we multiply by 1. But if we are decreasing by 1%, whatever C value we have only 0.99% of 0.99 of that particular value we have, right? So that indicates that what we are left with is 99% of the C value when it decreases by 1%. So we know that, right, we have this, right? This particular formula. V peak is basically equivalent to VA upon T1 upon RC, right? Now, if we are increasing this R, so we multiply by 1.02, right? We multiply by 1.02. And if we are decreasing this C, so we are basically multiplying whatever C we have by 0.99, right? So that indicates a 1% decrease in C value, right? Now, the other thing is to keep in mind is when we are doing a full scale conversion, right? RC is also a time constant, isn't it? RC, R multiplied by C is a time constant. So time constant, when we are doing this, right? So time, when we are doing a full scale conversion, T1 is basically equivalent to our RC, okay? T1 is basically equivalent to our RC. So T1 will cancel itself off with R and C values, right? T1 cancels, since RC is also our time constant. So this particular value will cancel off with T1, right? When we are doing a full scale conversion, what happens is T1 is basically equivalent to our RC, okay? Now, it says, now what happens is we have some constant multiplications with R and C, right? That is 1.02 multiplied by 0.99. RC will cancel off with T1. So what we have at the denominator, what will be left with is 1.02 multiplied by 0.99, which is equivalent to 1.0098, right? If you multiply these two constants, we'll be left with 1.0098, right? And since T1 cancels off with RC, so we'll have some digit left, right? And we are doing a full scale conversion, so our VA becomes 10 volt, right? So in that particular case, will be this whole formula will reduce down to VA is 10, right? 10, right? And the constants that were multiplied for R and C to indicate 2% increase in resistance and 1% decrease in capacitance gives us a value of 1.0098. This RC cancels off with T1, right? Since we are doing a full scale conversion, RC cancels off with T1. So we are left with 10 divided by 1.0098, okay? This 10 is equivalent to our VA, right? So our V peak value is basically equivalent to 10 upon 1.0098, which is equivalent to 9.903 volt. So V peak decreases from 10 volt to 9.903 volt, okay? Anyone has any questions regarding this? Or all of you understand what happened? Guys, you there? Okay, so you understand what happened, right? Okay, great. So no questions, right? Set. D, right? So this is the last part of this particular question. Does the conversion accuracy change? So like you know, when we are using a dual slope system, the R and C values are independent of the system, right? Isn't it? The accuracy of the system is not dependent on the R and C values, right? It does not depend on the R and C, I mean, change in R and C values, right? So basically what happens is, this is a lead up to this particular question, part C, right? Does the accuracy change? No, the accuracy does not change, right? In this particular case, what happens is this particular slope has an RC value. This particular slope has also got an RC value, right? If you go through the formulas, when you try to derive it, you'll see that this the RC, this RC value will cancel each other off, right? So you'll be only left with VP, VA, T1, and this T2, right? Whatever time you have for coming down. So it is not dependent on the RC value, right? If you had a single slope system, yes, then the system would have been dependent on the RC values, right? So any changes in the RC value does not affect the accuracy of a dual slope system, okay? I believe you must have learned this in your lectures as well. Moving on to question number 2, right? Moving on to question number 2. It says differentiate the two type, differentiate the type R to R. This is a DAC, right? It's not an ADC. So it should be R to R DAC versus binary weighted DAC, right? So we need to compare between these two DAC systems. So we need to compare between these two DAX systems. So you must have touched this in your labs, right? We have covered this in our lab. So this lab was covered last week. In fact, you'll be submitting this lab this week as well. So it is due this week, in fact, right? So I need you guys to actually differentiate between the two, and these advantages and disadvantages, something similar to this, right? Based on whatever you understood, should be in the discussion part as well, right? And in your conclusion, some bit should be in your conclusion as well. Now, let's just quickly go over the R2R DEX system and the binary weighted system, right? So let me just quickly go over the R2R and the DEX system, right, from your lecture notes. Do I have it here? Just give me a sec. Okay. So I have it here, right? So if you go over a R2R system, right, R2R ladder system, you'll see that this R2R ladder system has only two types of resistors. One is an R value, whatever R value you select, let's say 1K, and the other branch will be having 2R value. So what that means is if we are selecting R as 1 kilo ohm, the 2R will be having 2 kilo ohms, right? Isn't it? So when we are using an R2R ladder system, what happens is that this in this particular whole of this particular network, we just need two types of resistance, isn't it? One is an R value, the other one is 2R value, and we have multiple. We need just multiple number of this particular resistance, right? So we have only two different types of resistance, but we'll need different numbers of resistance as well, right? Like in this particular system, if we are having 4-bit conversion, right? So we'll need 1, 2, 3, 4. So 4, 5 2R values, and we'll be needing 1, 2, 3, and 4, perhaps 4 or 5 R resistance, right? So we just need two different types of resistor values, right, in an R2R ladder system. So what happens is if there is an error, right? Let's say we wanted to use 1K resistor over here in place of R, and 2K resistance in place of 2R. So if there is an error in one of these resistance, this will be same throughout for all resistance, isn't it? It won't change. Let's say we are using a 2K resistor for 2R value, right? 2K resistor. So in fact, the resistance will be having some sort of error in real world implementation, isn't it? You might have learned this in your EE 102 as well. The resistance of a resistor will have its a resistor will have some sort of tolerance, right? It will never give an accurate reading, right? If you are using a 1K resistor, it might give a 0.99 kilo ohm reading, right? So it will fluctuate, right? So what this means, if we are using two types of resistors, the error will be constant, right? It won't change with number of resistors, right? It will just propagate. It will be just normal, right? You are using two types of resistor, so the ratio between R and 2R will remain same, right? Nothing will change much, right? So whatever resistor ratio you will have for these two resistor will be same for these two resistor as well. Okay, so that is for regarding a R2R ladder system. For a binary weighted system, we go to a binary weighted system. So in a binary weighted system, you can see all these resistor values are basically of 2 to the power of n values, right? So let's say if we are using the first resistor as 1K, 1 kilo, second resistor will be 2 to the power of n multiplied by R value. So 1K, so the next one will be 2 to the power of 1 multiplied by R, so that will be 2 kilo ohm. The second one will be 4 kilo ohm. The next one will be 5 kilo ohm. So I mean, sorry, next one, 1 kilo ohm, 2 kilo ohm, 4 kilo ohm. Next one will be 8 kilo ohm, and so forth, right? But what you can see is this will change, right? What we'll need different types of resistance, right? Different types, like different valued resistance for each particular branch. It won't remain same. Okay, it won't remain same. So The first one has 1 kilo ohm, the second one has 2 kilo ohm, next 4 kilo ohm, 8 kilo ohm, 16 kilo ohm, so forth, right? It as the number of bits increases in that particular system. So what happens is, if there is some error in the first resistance, it won't give, this won't be same for the next one as well. There will be some error for R. For the first 1 kilo ohm resistance, the second 2 kilo ohm resistor will have some other value, some other error. The next one will have some other error. The next one will have some other error, right? So each resistor might have its own, like each different type of resistor value will have its own set of errors, isn't it? So what happens is, in a binary weighted system, all these errors will propagate, right? Will add up constantly. It will add up and create an errorless system compared to a R2R system. In an R2R system, we just have two types of resistor values. In a binary weighted system, we have multiple number of R2R, multiple values of resistors that will be needed to make up this particular network, right? So it is also difficult to maintain this particular ratio, right? This resistor differs from this by 2, right? This particular resistor differs by this by 2, or the R value increases by 2 to the power of n values, right? As you increase the number of branches, right? So that's regarding binary weighted 2R, R2R ladder system, right? Now going back to our tutorial question. So it says we need to differentiate between those two. So like I said, since we are using only two types of resistor values in our R2R DAC system, it is much more easy to implement, right? It is much more easy to implement. Since we are using only two types of resistor values, so a error will not propagate itself, right? So we are only using two types of error. So whatever error we have in each resistance, it will remain constant for the number of resistors that we are using, right, in this particular system. So the system will be more accurate compared to the binary weighted system, okay? We are only using two types of resistors in a R2R ladder system. So the error will be much smaller compared to a binary weighted system, because in a binary weighted system, we are using multiple values of the resistor, right? So different kinds of resistors are to be used in a binary weighted system, okay? Now, since the system is easy to implement and it is much more accurate, it is well suited for a IC realization, as it requires matching of only two resistor values, right? Only R and 2R. So it becomes much more easier, or much more well suited for a IC realization. Now, going for a binary weighted system has multiple number of resistors that that will be needed to be used, right? So not just two types of resistors, just in case of a R2R ladder system, right? In a binary weighted system, we need different values of resistor, right? So this will vary as the number of bits in the DAC system increases, right? So the number of resistors required will also change. So as stated over here, the disadvantage of this particular system is that for a large number of bits, right, for n is greater than 4, the spread between the smallest and the largest resistors becomes quite large. So when you are using 5-bit system or 6-bit system, the spread, right, if you are starting with 1K resistor, so then the fifth bit and the first bit will have a difference of 2 to the power of 4, right? So that will be basically the resistance difference will be of times 16, right? So we need different types of resistance to accommodate this, right? So the spread between the smallest and the largest resistance becomes quite large. Difficulties in maintaining the accuracy of the resistor values. Like I said, we are not just using two systems, right? Two ratios or two types of resistors. We are using multiple types of resistors, and each resistor has to be a multiple of 2 to the power of n, right? 2 to the power of n minus 1, right? Value. So it's quite difficult to maintain the accuracy of this system. Second point is need to have accurate resistor ratios over a wide range of resistors. So in this particular case, in a R2R system, we just have two resistors. So whatever resistor we have for each particular branch, whatever ratio we have, it will be constant for each particular branch. But in the binary weighted system, since we are using multiple weight and multiple different types of resistors, So the ratio has to be maintained, right? So it is quite difficult to maintain that. So the first one will be 1K, let's say, right? The second resistor should be 2K. The next one has to be 4K. So it is quite difficult to maintain the resistance, right? Like I said, in a real world implementation, if you're measuring a 2K resistance, the value of the 2K will be different compared to 1K. I mean, compared to the actual value that is given by the manufacturer, isn't it? It won't read as 2K. It will give a smaller or a larger reading, right? It won't give you precisely a 2K resistance, right? At times it will happen, you'll get 2K resistance, but it is not necessary that you'll be having 2K resistance, right? So that's regarding this particular point, right? Then switches in series with the resistors require zero offset voltage and low on resistance. So I would say that this is common for both, since we will be using resistance for both the cases, right? So switches will be used, right? Current drawn from the reference varies with different pattern, causing change in voltage drop in Thevenin equivalent source resistance of the reference, leading to a data dependent errors called superposition of errors. So what this particular statement says is the current drawn from the reference varies from the input pattern, right? So what this is an indication. Like I said, that there is a different. We'll be using different types of resistance in a binary weighted system, right? Isn't it? So the error with each resistance will change, right? It will change. So if you are using a 2K resistor example, right? For example, if you are using a 2K resistance, you won't get the 2K reading, right? When you are actually you're implementing the circuit, you won't be using a 2K resistance. It will be somewhere around 1.8 or 1.9 kilo ohm resistor, right? So that resistance, right? Since we are using multiple resistance, it will propagate, right? So the resistance changes, right? Whatever you have calculated, that value compared to the actual implemented system will be different. So the current drawn will be different and it will vary, right? It won't be constant as to what you have calculated, right? The current drawn pattern will change as well because of the error in the resistance, right? So the current drawn from the reference varies with the input pattern, causing change in voltage drop, right? So current, resistance, and voltage are all tied up together, isn't it? In a Thevenin equivalent source resistance of reference, leading to a data dependent errors called superposition errors. Like I said, we are using multiple types of resistance in a binary weighted system. So the error with each resistance will change and it will all be accumulated and it will superimpose the error in the system. Okay. So that is what this particular statement means. So anyone has any questions regarding this? So all of you understand what a binary weighted system is and what a R2R system is? Guys, you there? Hello? Okay, great. So all of you understand it, right? Let's move on to the final question. That is, for a counter type ADC, if the conversion time is around 4.1 milliseconds, right? The conversion time is around 4.1 milliseconds, then the minimum number of conversions that could be carried out each second would be approximately, excuse me. So basically what we know is that each conversion takes 4.1 milliseconds, and we need to know how many conversions could take place in 1 second. So basically that would be 1 second divided by 4.1 milliseconds per count, right? So that is going to give me 244 counts, right? So basically we can do 244 conversions. That is the minimum number of conversions that could be carried out by this particular counter type ADC, right? So with that, we conclude this week's tutorial, right? So anyone has any questions?
So I had a question regarding the lab.
Okay, so we'll discuss this after this, right? So regarding the tutorial, there's nothing, right? I believe. So with that, we'll conclude the tutorial, right? And yeah, with that, we'll conclude this week's tutorial.